So I just remind that why we need to consider, why we need to increase this inflation stage due to the fact that Friedman elementary cosmology has some problems, and one of them, this is flatness problem of cosmological horizon, problem of magnetic poles, and others. So, and the idea is that we need to solve this problem. We need to consider to use to put something, some additional stage of the universe, which was very early, before the stage which we considered before. So, and that means that we need to, because what we have only, with this. I would like to say in advance that in the energy density of cosmological term for the inflation stage is different. So, and it's it means that we need to apply this equation of state that to allow, you can say like this, to allow the space expand exponentially. So now I would like to speak about physics of inflation. Let's put it physics. Inflation. The cosmological term can describe some scalar field, which called the field of inflaton. So we can suggest that universe consists, or there is such a scalar field. For example, we can call it like a phi. So, and you can see that in general case, it can depend on a radius vector and time. So this is correspond to the field of inflaton. So it's not a plankton, because I remember that once on exam some girls say there is a field of plankton. So plankton, this is different. This is what is existing in ocean. So this is inflaton. Just some term which useful, which we use when we speak about cosmology, such a kind of field which create acceleration of the space in the universe. So let's consider that the potential of such a kind of field, let's call it V. And if we will consider the energy density, so this is related to already, to the quantum theory like this. So when we consider such a field, scalar field, for example, there is just for some connection, we spoke about black holes, but also there are such a kind of object which predicted in general relativity, which called naked singularity. Naked, it looks unbiased. So, and means that it can exist possibly object without even horizon. So, and only with singularity r equals 0. But the problem is that such a kind of object exists only if there is such a scalar field in universe. So, and this is under debate, can this object really exist or not? So let's consider the energy density of inflaton, and this is we can write analogy with with a quantum thing, so we will put here the Planck constant C cube, just, you know, to succeed with the dimension, plus V. So you can prove simply that the dimension of this one, why we put this constant, the dimension is energy divided on L cube. So you can see it. If we, the dimension of phi, we consider as energy, the dimension of is energy. So for this energy density of inflaton, so, and I put here phi just to remind this is inflaton, the pressure will looks like square minus V at phi. And we can see that if the field on inflaton change very slowly as a function of time, so in the case if phi square much less than this value, in this case we will have exactly the equation of state which we need to, so because as we remember, so this is exactly the equation of state which create the exponential change of the scale factor. So in this case, if condition satisfy, this scalar field, some distribution of scalar field, can create exponential inflation. Again, you can write in your conspect if phi point is the small. For phi point, this is, I will remind that when we use the point, means d phi by dt. Okay, derivative time. Also example of the scalar field. For example, the scalar field describe bosons. Bosons, this is a particle is important to this again. Interaction carriers. So so I can tell it. This is particles, переносчики взаимодействия. So bosons has, for example, they have a spin equal 0. An example of the bosons, this is, for example, the Higgs particles, about which we spoke on the previous lectures. Or, for example, for electroweak interactions, this is W plus minus Z bosons, which is important to, which they are responsible for the electroweak interaction. So this is and when we are working with such a kind of particles, so they are also, you can describe in the term of scalar field. And so in this case, we also working with a scalar field, which can be also can be responsible for such existing of such particles. But for now, we speak about some scalar field. We don't know exactly what is it, but one of the ideas that it can be the energy of vacuum. which create such a kind of the physical point of view. So this can be the energy of the vacuum, because vacuum is not empty. When we speak about a vacuum, it means that we have virtual particles which connect with each other, annihilate, and like this. And vacuum has also energy. And one of the ideas that it can be some unstable form of the unstable physical form of the vacuum, which create such a kind of dynamics in the universe. So we, in principle, I just want to show you some equation, which in inflation cosmology is very important. It's also finally bring us to even to the idea of multiverse, multi-universe, which we'll speak a little bit. So, for example, let's find the equation for the scalar field. And in principle, we can use the equation which we obtained from the first law of thermodynamics. So this is, look, you can refer to the lecture which we had before. So I have a little time why I try to do everything quickly. And if we will put here the expression for epsilon phi and p phi, so we can, just a second, I have a message. Okay. Okay. So we can find that epsilon phi point, which is, the epsilon phi by dt. So if we will just find the derivative of this expression, we will have what we will have. So 1 divided h c cube phi point phi 2 point plus dv by d phi point. Okay. And now let's, what we will have. We will have 1 divided h c cube phi point phi 2 point plus d by d phi point plus 3h and and here we will have if we will consider the sum, so we will have this one, phi point square equals 0, like this. Or we can simplify it because we can see that we can divide on phi points. So finally we can obtain phi 2 point plus, and I will multiply on hc cube 3h phi point equal minus hc cube dv by d phi. So this is of inflation cosmology, which tell us that the evolution, because we consider that phi this is a function of t, and in principle it's not important to consider the dependence of r, because we consider that and also h also the function of t. We can see that the equation of, we can call it equation of evolution of scalar field, that it's like a equation of harmonic oscillator, but this oscillator with a friction. So as you remember, the equation of friction has such the same plus a x point equal minus kx, like this. So it means that it looks like this equation looks like oscillator with a friction, and that acceleration started with a force which proportional minus dv by dv, but the continuation of the motion prevent the friction from another side, which proportional to the velocity, speed of the particle. So what it means? It means that expansion of space in the universe is provided by, is called like a Hubble friction. So Hubble friction, this is related with the summand 3h v point, which really decelerate the passing from the field of Planck to the minimum value of potential. So we can, in principle, we can write it on some schema. Is it write some sketch. So if we have a field with such a potential, and in the beginning of the even the beginning configuration stage, the potential field, potential energy of this Planck scalar field is enough high, so we satisfy this condition. Okay, so like this. So now I have some from department registered about your registration in Moodle. Okay, we will solve it later. If we will have some difficulties, I will write you in any case, I will write you in Telegram. Now let's finalize the lectures. So in this case, we have some condition which called like a felt vacuum. This is the structure of this scalar field, which looks like this. So we have some unstable condition, and this you know, this slope of this function is very small, so it's slowly going down, and this is exactly correspond to the inflation stage. Now, Alessandra, but now for seminar, what you go in which place now?
To the seminar, with the astro meeting. You forgot about.
Yeah, I have now my lecture, but about what seminar?
It's about the fall of antimatter. So it's antimatter. Yes.
Super.
It's interesting. That's what we should have done, but you're also busy.
Okay, maybe you can give me a later some. Yeah, some. I'm sorry, I need to analyze my lectures today. Okay. See you later. So you can see I could go to listen something about antimatter, so but So this is a condition which call true vacuum. So it's a or истинный vacuum. And the idea that you is that the state of the vacuum, and it's tried to reach as usual, you know, system try to reach the stable condition which correspond to this point. And the inflation stage continue this part with finally falling down in minimum of potential energy. This is an idea. So, and when we speak about Big Bang, I mean that was a point, and maybe you could hear a lot about Big Bangs of the universe, when the universe became very hot, and after this, as we discussed, it expand and became colder. And one of the equation of also Friedman cosmology, and why what's exactly creates a universe with a hot condition. And the idea is such a way that when the universe reaches this state, so it was an oscillation around this, you know, when it looks like if you will put a ball here, so this ball will go down and oscillate sometimes in this minimum of the potential, and this oscillation of scalar field create exactly the kinetic energy of this oscillation, create and iterate to the heating of the universe. So if we speak about Big Bang, this corresponds exactly this point. So sometimes even the people create the beautiful posters about the evolution of the universe, which are not correct, in sense that inflation stage was before Big Bang. So this is just what I wanted to say. And the theories, there is not one sort of general inflation stage now is real, because with this inflation stage we can explain many problems which we have in Friedman cosmology. We even find the reason why universe became hot, and the reason again this is this inflation stage, and after this go down to the minimum of the energy. I can suggest you to read the book, which is very beautiful about writing like a popular book, Vilenkin. Many worlds in one, like in English. There is a translation, but only in Russian language, not in Ukrainian, unfortunately. But so you can, if you would like to read it, you can use so. I can advise you any books in Russian language, but in principle, I can tell that you can find the translation also. It's a beautiful book. By the way, Vilenkin was graduated in our university, and after this he goes in America, in Moscow, America later, and he's one of the great cosmologists of our time, and he exactly was working, continue to work with this inflation stage of universe, and he popular way this unstable state in compare it with the situation of the drunk person. So very funny and very interesting. Also, as Vilenkin and Linde, Vilenkin. Linde was a Soviet Union physicist, cosmologist. Later, he also go to to United States, as I remember correctly. It's a very great also physicist who is working with inflation stage. It's interesting that finally the idea of inflation is bring us to the idea of multi-universe. So so I will, if I will have time, I will speak a little bit later. Okay, this is just to understand what it is, and the inflation stage can solve the problem about which we spoke. For example, the flatness problem. We can solve immediately. Solving of problems of Friedman-Lemaitre cosmology or model. So the flatness. We can solve it immediately because it's understandable that if even at the beginning we had some curvature of the space, some complicated curve space, due to inflation, this curve of the space will disappear because due to the fact that expanding which we have really very fast and big. So if you have some curved, for example, piece of paper and carbon, you can stretch it, and finally, of course, all curved parts will disappear. So this is immediately solve the problem of why, and the answer why the space in the universe is flat. So due to the fact that the space stretch very quickly and very huge. So second one, for the second one, this is magnetic monopoles. So the idea that we can prove that if we apply the inflation, for example, we obtain that the concentration of monopole on grand unified theory energy, which corresponds to the initial time of inflation. This is 1075, right? Check. Yes, this one. So we can see that since we decide to start inflation, the initial of inflation is equal T good. So this is approximately 10 minus 36 seconds. And we also decided that it's enough, let's consider it's enough to do it during this time, the finish inflation, like this. We can obtain that n monopole on T finish. We can estimate it simple way that n monopole T initial, and due to the stretch of the space exponential law, we need to put here L cube. Okay, so it will be 3n. If you put here an initial like this, so finally we obtain the number minus 54 centimeter minus 3. This is the end of inflation. So, and it means that starting from this time, finish to 0, we have just a normal Hubble expanding. Expansion. So, and we can just use for example, the formula for the radiation stage. So we can use that A. Like this, we obtain this formula, and for the as you remember, we put it. We obtain even this number. This is 10 minus 27. So this is scalar factor for the end of the inflation. And we can, for us, it's interesting to see which will be the concentration of monopoles for the present time. So we can find it as a concentration of monopole on the end of the inflation, multiply on this. Just we can find through the consideration of the ratio of the concentration of monopole for the present time and for the end of the inflation, and depends on scale factor. So it will be like this. So we know everything. If we will put all of these values, we will obtain 10 minus. It's an incredible number, but this is cosmology. So this number and if we will consider it to transform this in megaparsec and cube, so you can check it, we will have 10 minus 51 1 by megaparsec in cube. So this is what we obtain due to inflation. So we can see as a result that it's impossible to meet even one monopole in 1 hour in our casual space, because it's a very rare. So the concentration is incredibly low. So it means that we can't exclude the theory of grand unification when, for example, predicts the existence of the monopole. In principle, we don't see such a kind of particles because they are really very rare. So you can see that concentration is incredibly low, and maybe we even don't have one monopole in our casual region. It's far on the far distance. So this is the solution of magnetic monopole. And the third one, this is the problem of cosmological horizon. So the problem which we discovered is that if we will work in the trigonometric cosmology, we will see that if we go in the past, we could see that we need to have a lot of non-causal region which can't connect with each other, and it's a huge. And it means that it's against of cosmological principle and recent observational data for the universe, because we can see, because there is equation, but why universe became homogeneous and isotropical if sometime before it was really a lot of non-causal region. So, and the inflation stage solves this problem. How we can see it? So let's remind that the radius of our casual причинно связанная region H0, I don't remember, maybe we call like this, and we calculate it. This is 1028 centimeter. So if we will, since we can immediately to calculate which size had our causal region on the end of inflation. So to do this, we just need to make it more simple calculation. So this is the finish. We found it before because, as you remember, we needed to use for this the dependence of scale factor. Okay, we exactly obtained it here. Scale factors 1 for the radiation stage. So, and so we need to do like this. Okay, so this is A finish multiply on this LH0, H0 for T0 for the present time. And we have 10 centimeter. This is end of inflation. So it means that if we will consider which scale our causal region had on the end of inflation, it was 10 centimeter. So everything was inside 10 centimeter. So it's like sometimes look, the people say it looks like you know, this the volume of the orange fruit, or like this. If you will consider the end of inflation, see, this is, yes, end of inflation. Let's put here like this. So we can take this number and decrease it, and let's we can consider it not very precise, but so but we obtained the expression for the scale factor, how scale factor was changed due to inflation. And look, this one exactly what we need to use. So minus 33. So it will be 10 minus 32 centimeter. So this is beginning of inflation. Let's consider, so this is the scale of our causal region for this time. If we can consider the horizon scale, we can consider the for the L, and look, I will not put here 0, because when I put here 0, it means that I speak about exactly our region. Okay, just I want to calculate the horizon scale for corresponding time. So this is Ti for the end of inflation. Very simple. Speed of light multiply on 10 minus 36, which is the beginning of inflation. So in this 10 minus 26 centimeter, and LH finish, CT finish. We even can make not like this, so we can take. We know that the space change on 33, LH initial, so it will be 1033, 10 minus 26, so it will be approximately 17 centimeter, or approximately 0.1 parsec. Now, if we will consider this value for the end of inflation, in this value, you can see that LH much more than LH0 for this, for the time they finish. If we will consider this one and this one, we also can see that the same the initial. So for this case, we can see that the horizon for each of this time, the scale of cosmological horizon, much more than the scale of region, our region, which we consider on this time. So, and this solves the problem of cosmological horizon. And this is one of the answer why our space is homogeneous and like this. So, because when we go in the past, the horizon, cosmological horizon, much bigger than the scale of our causal volume for this time. So about others problem also can be solved because, for example, the problem which connected with the equation, but how the large scale structure appeared, what was the seeds, the beginning of the formation of this large structure. So we can speak about quantum fluctuation, and this quantum fluctuation in the inflation stage, in the beginning of inflation stage. So this quantum fluctuation, they stretch to the macroscopic scale, and they created paired such a kind of this scale structure, which evolved finally in the large scale structure of the universe. And now, in principle, now as a recent theory, they allow to grow up the large scale structure, put as a seeds some initial condition on the level, even the quantum fluctuation, and of course correspond and compare it with observational data. So this is of course a great idea, because great things, because we really can jump in the time, which is impossible to imagine before. In sense to try to explain even the formation and even the creation of the universe. So this is what I wanted to say about this. Also, there is an idea we called why? Okay. Very interesting. This program doesn't want to create the page with the number 101. Is the limit? No, I don't like it. Okay. Let's move on. Okay, there is a idea and model theory which is called chaotic. Okay. Chaotic inflation. You remember that you hear yet? Can you hear me well?
Yes, we can hear you.
Okay, maybe what I said before looks like fantastic, but this is recent cosmology. We also discussed some problem of anthropic principle. I maybe didn't anthrop. Okay, through TH anthropic principle. There is such a kind of problem which call anthropic principle, and there is the general idea is such a way that why is everything in universe the fundamental constant and like such way that, for example, if the mass of proton will be different from the value which there is now, and the ratio of the electron mass, proton mass will be different, so we couldn't have such a kind of stable system as the stars like this. So, and so on. It's there are many reasons finally to make a conclusion that the universe looks like universe created exactly for the case that in this kind of universe observer could appear. So it means that if we would like that the universe could appear such kind of complex object as a human, as a, as a man, as a human, English use the word man. So and woman, of course. So some intelligent life, it means that we consider us as an intelligent life. So it means that fundamental physical peculiarities of this world should be balanced with each other. This is the main idea. And and this was sometimes ago it was really a problem, and of course the religion and Pope they were happy because look, they said when it was discovered that if you will move a little bit this fundamental constant, this fundamental ratio between elementary particles like this. So finally, we can see that the Earth, the life on the Earth, which has a complicated structure, will be not appeared because we need especially the special star as the sun, which need to live for a long time. We need to have planets around, which we need to have the heavy elements. They are a product of evolution of the stars, and evolution should be long and stable. Finally, stars which we have now and our sun should be stable like this. So, but if you will change the fundamental numbers, I can say like this, you will not have such a kind of the world. And it was one of the questions. The idea of and the solving of the anthropic principle, why, of course, the church was happy because they said, okay, it's understandable why, because God wanted, he was, he was alone, and finally he decided to create the person, intelligent life that can help him to not to be annoying and to investigate the universe, the world which God created like this. So, which is, as we discussed, for us, for scientists, this is not a good answer on this question and the solving of this problem. This problem can be solved in the framework of chaotic inflation. You can also find in popular way this description in the book of Vilenkin, The idea that this inflation can switch on with different condition in different places of the space. So, for example, schematically, we can consider like this. And there is a condition in this space, in this, and this, and this. Here we have one law of inflation, the second law of inflation, the third law, the fourth law. So we have, and this volume, let's call it volume, they are not connected to each other. So this, for example, one of this just finally created our universe where we are living. But it can be also different universe. Is a different condition, which is different from condition in our case. And why we have exactly such a kind of constant? So it's just inflation 1, inflation 2, inflation 3, and so on. Why we have a special condition that finally man can appear and have a really complicated form of the life. This is due to the fact this is by chance. So this is by chance. Exactly, we are in such a kind of universe. So this is our universe. We just can't appear in this universe or in this universe because in this world they have different condition. But we are here because this is not something special. This is one of the universe which has a condition to create a more complicated form of life. This is the idea called multi-universe. So like this. And it's related with chaotic inflation. Of course, I don't write any formula like this. I just want to say is that as soon as we suggest and we create this inflation, in principle, you can see that there is a solution for such kind of model. So it's an so it's not forbidden from the point of physics. Otherwise, there is such a kind of solution. And this is the point. Let's solve this entropic principle, which was one of the really problem times before. Now, now we have an answer on this question. Oh, okay. This is about inflation. Maybe I will finish on this. I just also want to say a few words about stage of the universe, which join important end in universe, which for us really important. So now we quickly can consider the stage of the universe, which is complicated to consider quickly because the main idea is that, again, that each stage of the universe correspond to, the physical stage of the universe before we consider a dynamical stage. When, there is a change of the law of changing of scale factor. So now we will speak a little bit about the physical properties, physical stage of the universe. So one, and we already spoke about this. This is correspond to theory of everything, this energy. So which correspond to the Planck scale. We can speak about this time, we can speak about the appearing of including our world too. So if we will speak about the particles, so they are in principle almost doesn't exist, so they, you know, created an and like this. I have the energy is incredibly high, we considered it before. So this, in this case, we have particles and antiparticles, matter and antimatter. Now exactly seminar about, not about this, I think about registration of antimatter. So the second, this is the grand unified theory energy. So as we remember, we consider this time, and this approximately consider, say, beginning of inflation stage. So the t around 10 minus 36 second. What is important that possibly on such a kind of scale, the gravitational field came free, but we have together the strong, weak, and the electromagnetic interaction. Possibly, so in principle, the next, okay, let's put it next stage. We can consider the next stage as energy of quantum chromodynamics. So this is, maybe you even had lectures about quantum chromodynamics, you know. This is exactly, this is approximately the energy 10 giga electron volt. What is important on such a kind, approximately such a kind of this energy, that approximately in this energy we have, for example, now we know that the number of baryon particle to the number of gamma quants approximately 6 on the 10 minus 10. So this we called of baryon number. And gamma, this is CME gamma quants. Okay. B, this is called, this is, you know, arc baryons. So for the present time, we have this value. In principle, we can see what it means. It means that how this gamma quant appeared. On this early stage, we had particles and antiparticles. So in principle, we had a quark and antiquark. They annihilate with each other, create gamma quant. So if, for example, the number of quark and antiquark will be the same, finally, all of them could annihilate and no any ionic matter. Only photons at all. This number tells us that, and this kept this number is kept due to the stage. It tells us that on the early stage we had okay, let's consider 10 minus 9, for example. On one it's a billion, okay. particles or antiparticles. It was 1 billion plus 1 particle. So this number, particles and antiparticles annihilated with each other, created gamma quant, and only one particle on 1 billion was finally kept, and as a result create the matter which we observe now. So this is a point. It was a really a special time, special moment. We call about we can consider it like a phase transition. So we can call it spontaneous symmetry breaking, because possibly before we had a really equilibrium between particles and antiparticles, and finally this equilibrium was broken, and as a result we had this moment when 1 billion antiparticles with 1 billion plus 1 particles, which finally allow not all particles to annihilate. And this particle create the recent matter in the universe. So this is a point. What else? So we have what important because you know the time of the universe so divided on some Lepton era, which correspond to energy, which is related with such kind of process, which are related, for example, for hadronic particles, for leptons. What I wanted also to say, so I don't have a time to speak about you, unfortunately, but I want to say also about, just to feel it. Let's put it on drone. Hadronic. Yes, hadronic. Hadronic stage. So hadronic stage is related with important processes that are related with hadrons. What is a hadron? This is protons. So this is a paradox of nuclear protons, neutrons, and important event which was really in this time, and the reaction which was in this time, it's annihilation proton and antiproton, neutron and antineutrons, like this, with the creating of the gamma quant, which again, these gamma quants are exactly this cosmic microwave background. So the appearing of this CMB, it was during this time. Finally, it became free later, but this is the reason why the potency period. What else was important? Because we understand that protons and neutrons and like this and particles, you can, if you speak about ions, they consist of the quarks. So, and when the universe were very hot, very energetic, the quarks were in a free condition. So we can even, sometimes it's called like a quark soup. And on energy, approximately 300 mega electron volt. Sometimes we speak about 200 mega electron volt. It was very important event. It's such a kind of confinement confinements of quark. Confinement, it means that now the quarks can be kept inside of the particles. So this is really fundamental, because the point that the elementary particle are stable is very important for the stable of the matter. So it could be really not beautiful for the life if, for example, the energy to destroy protons or neutrons will be not so high but low. It means that in this particle couldn't exist for a long time. And this event appeared in this time, confinement of quarks, when quarks really create the baryons, the elementary particles. And it was important because starting from this time, when energy became less than this value, so the particles became stable, and it can already start to participate in next level of processes. So this is what I wanted to say. There is also lepton stage. Here in lepton stage, this is energy which correspond to annihilation electron-positron pair. And it's already understandable that this stage is related with a connection between light particles as electron or muons, like this. So also on this stage, annihilation electron and positron pairs. The energy of this stage correspond to the energy of the annihilation of electron-positron pair. So we can, it's approximately, even exactly, this we know exactly, 511 electron volt. So I can put here this corresponding of annihilation with the appearing of 2 gamma quants or even 3 gamma quants. And on this stage, of course, photons also are dominated. So like this. Okay, let's finish on this point. I want to reach the end of the discussion of the seminar, which is now. And let's consider in the next lecture, I will show you some picture and I will speak about predict emission, which appeared in the end of the radiation stage. So we will speak about also maybe large scale structure. And I don't know, I showed you large scale structure in simulations.
Maybe no.
Maybe no. Okay, so let's see it. Okay, now I will make a okay, see you on when? 3 p.m. Yes?
3:20 p.m.
3:20. Okay, 3:20. right? Okay, 3:20. Okay, see you 3:20. Maybe I will know something about exam. Exam we will have on Monday, right?
Right.
Okay, and which time?
1 second.
At 12.
12. Okay, 12. Good. Okay, see you 3:20. So if you will have some question, you can ask. Okay, bon lunch.